Hello there! Welcome to Lecture 27, Color. Visible light waves with different frequencies appear as different colors of light. When light waves reflect, transmit, absorb, or scatter selectively based on their frequency, objects take on different colors. This can explain many topics, from how color monitors and phone screens work to why the Earth's sky looks blue. Each of the following concepts will be discussed in this video: color, transmission, absorption, and reflection, color addition, color subtraction, and scattering. The visible light section of the electromagnetic spectrum encompasses light waves from red to violet. Perhaps you've heard the acronym ROY-G-BIV, which stands for red, orange, yellow, green, blue, indigo, violet. While visible light is better described as a spectrum rather than as discrete quantities, we consider ROY-G-BIV to be the major colors of visible light. What distinguishes each color is the wavelength of that light. Red light has long wavelengths, green is in the middle, and violet has the shortest wavelengths of visible light. Human eyes contain cone cells that allow us to perceive light. There are three types of cone cells: one sensitive to short wavelengths of light, one sensitive to medium wavelengths, and one sensitive to long wavelengths. When light waves of different wavelengths and intensities interact with our cones, we perceive things as taking on different colors as a result. Physical or inherited issues with cone cells can be a cause of color blindness. The three primary colors of light are red, green, and blue. Using color addition, which we'll discuss in a few moments, these three colors can be combined to generate all other colors of light. When we look at objects, we don't actually see the objects themselves. We see the light that reflects off of them into our eyes. In the case of transparent objects, we see the light waves that transmit through the objects. We'll discuss reflection in more detail in the next lecture. For now, it's sufficient to state that reflection is what occurs when light waves bounce off of a surface. When we look at something blue, that means that the blue light is reflecting off of the object into our eyes. Red and green light waves are absorbed by the object, which is why we don't see those colors. A red object reflects red light and absorbs blue and green light. In general, objects that reflect light into our eyes reflect the colors that we see and absorb the colors that we do not see. Transmission occurs when light waves pass through an object. When we look at blue transparent objects, those objects transmit blue light and absorb green and red light. When we look at a yellow transparent object, it transmits red and green light and absorbs blue light. Other objects that we see via transmission of light are light sources themselves. This includes light bulbs, LEDs, traffic lights, street lights, and so on. Red light bulbs transmit red light waves to our eyes. Green light bulbs transmit green light waves to our eyes. Objects that we see via light transmission transmit the colors we see and absorb the colors that we do not see. Color addition refers to the ability to use light to create secondary colors from primary colors. Mixing various intensities of red, green, and blue light allows us to create any other color of light. Color addition is related to light we see via transmission. When two primary colors are transmitted together, we see a secondary color. When red and blue are added, magenta is created. When red and green are added, yellow is created. When blue and green are added, cyan is created. Magenta, yellow, and cyan are therefore known as secondary colors. When all three primary colors are added, the result is white light. All other colors can be generated with mixtures of red, green, and blue light at different intensity levels. The video you're watching right now is defined with an additive color model, as it is intended to be watched on a computer or electronic device screen. An LED display contains tiny pixels of red, green, and blue LEDs. An LCD display contains red, green, and blue light filters. The mixture of red, green, and blue generates all of the different colors you see in this video. This demonstration uses RGB, red, green, blue, light-emitting diodes to show color addition. The top dial changes the intensity of the red light, the center dial changes the intensity of the green light, and the bottom dial changes the intensity of the blue light. When I turn on red and green, the result is yellow. Red and blue makes magenta. Green and blue makes cyan. Finally, I turn on all three colors, and the result is white light. When it comes to light and color addition, white, as mentioned, is generated when all primary colors are mixed at equal intensities. The color black is perceived when there is no light at all. In that manner, black can be considered the absence of colors. While color addition pertains to light transmission, color subtraction pertains to light reflection. Subtractive color models are used primarily in print. When you look at a color magazine, book, or poster, you are seeing the light waves that reflect off of the pages and into your eyes. Color subtraction refers to the colors that are absorbed by pigments or other printed material. Cyan absorbs or subtracts the color red. Magenta absorbs the color green. Yellow absorbs the color blue. Secondary colors therefore subtract out primary colors. Through this color subtraction, other colors can be generated. When cyan and yellow are mixed in a subtractive model, blue and red are subtracted, and the result is green. When cyan and magenta are mixed, red and green are subtracted, and the result is blue. When magenta and yellow are mixed, blue and green are subtracted, and the result is red. When cyan, magenta, and yellow are mixed, the result is black. Color printers work by using separate cyan, magenta, and yellow inks. Usually, a separate black ink is used to generate black without using excessive amounts of cyan, magenta, and yellow ink. If you've ever heard or seen the term CMYK, that refers to subtractive color: cyan, magenta, yellow, black. Selective transmission, reflection, and absorption explain the colors of most things we see on this planet. But some phenomena require the concept of scattering to explain. Scattering is a process where the direction that light travels in is changed without affecting the wavelength of the light. For example, why is the sky blue on Earth? The Earth's atmosphere is composed of many particles of different gases, as we discussed in Lecture 14. When light from the sun travels through these particles, due to the size of the particles, short wavelength light is scattered more efficiently than longer wavelength light. Atmospheric scattering causes short wavelength light, such as blue and purple, to reach the surface of the planet. Our eyes are more sensitive to blue than purple, therefore we perceive the sky to be blue. Cloud particles, being larger than atmospheric particles, scatter longer wavelengths as efficiently as shorter wavelengths. This makes clouds appear to be white. On overcast days, the sky appears gray, a muted shade of white. During sunrise and sunset, the sun's shallow angle with respect to the horizon means that light from the sun has to travel through more atmosphere than it does at other times of day. When sunlight travels through so much atmosphere, so much blue light is scattered away that the effect is a red sky. In this demo, a fish tank is filled with water. Some milk is mixed inside to act like the molecules in our atmosphere. A flashlight acts like the sun, providing a white light source. When a flashlight is directed into the milk-water mixture, the short wavelengths of light, notably blue, are scattered immediately, and the long wavelengths of light, orange and red, continue to pass through. This is similar to what happens at sunrise and sunset. If the color of the sky is explained by our atmosphere, then what happens on celestial bodies with no atmosphere? On the moon, for example, there is effectively no sky. The sun appears as an orb in space, and the surrounding areas of space are black. photos from moon landings depict the darkness of space. The atmospheric composition of Mars leads to a brownish pink sky color. Mars landers have taken color photos depicting this fascinating sky color. Thanks for taking the time to learn about color. Until next time, stay well.